Hello, my name is Kevin. This is Lab 3 Magnetic Field of a Bar Magnet. In this lab, we'll be measuring the magnetic field at different distances. This is to see how distance relates to the magnitude of the magnetic field. From the experiment, I measured the average off-axis magnetic field is 8.05 times 10 to the negative 5 teslas. The formulas I will be using in this lab is the Boyd-Savarт law formula. This is to help us calculate the magnetic field of the bar magnet. The second formula here is to help us determine how the distance affects the magnetic field. And this third formula here helps us change our graph slope into usable data for our distance dependence formula. The main physics ideas that we'll be dealing with is the Boyd-Savarт law. This helps us determine how strong the magnetic field is, and then magnetic fields as well as magnetic dipoles. As with these bar magnets, they have a north and south, and we can equate this to it being a dipole. And that can help us figure out which direction the magnetic field is pointing. In this lab, I wrote down the different distances at each specified Tesla values. I did the same at 20, 70, 120, 170, and 220. And then on the bottom, I did the second part of the lab where we find the distance perpendicular to the magnet. And with that, I wrote down the different y values. To find by corrected, I subtracted by earth from by measured. The first formula we used here was a linearization formula, where we could find n and k. This linearization formula reflects the same data given to us as the slope formula. So in this case, we can use n as a slope. So n will be negative 2.5343, and this is from the Excel on the right side. To find k, we can set that ln k is equal to negative 13.645. And with this, we can take the opposite of ln, which is e. So we can raise e to the power of negative 13.645, and that gives us a k value of 1.185 times 10 to the negative 6. To find mu, I set the two formulas from the last slide equal to each other, the Boyd-Savarт law and the distance dependence of the magnetic field. To find mu, I set the two formulas equal to each other from the previous slide, the Boyd-Savarт law formula, as well as the distance dependence formula. And with this, we can move the formula around to have mu by itself. And with this, I got 10 to the negative 7. That is the constant from mu naught over 4 pi times k rn plus 3. The n plus 3 came from moving r cubed to the left-hand side and divided by 2. To find mu, I plugged in k from the work above and n from the work above as well. And after just plugging it into a calculator, I was given 5.929 Newton meters per Tesla. This was the code. This first picture here is making the magnet. I did two things here in the first picture. First, I plugged in my mu magnitude, which was from the work we just did, 5.93. The second thing I did was create the function for the magnetic field. This was just plugging in the formula. The second picture here is defining the observation points and then making the on-axis arrows. The third picture here is making the off-axis arrows. Here on the left-hand side, I finished off the code with making the 45-degree arrow. All of this was pretty similar to the other arrows. The only data he plugged in here was the distance perpendicular, which was found on the experimental data sheet. I just plugged in the average perpendicular distance. On the right-hand side here is the model that I was given. You can see the blue arrows pointing to the left-hand side and the orange arrows pointing to the right-hand side. The blue arrows are the perpendicular axis, and the orange arrows are on axis, and the purple arrow is the 45-degree arrow. So some assumptions that we made is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Some possible errors that I could have made were measuring errors. Another error I could have made was a setup error with the magnet and the meter stick. I could have made calculation errors, and another error specific to this lab was if I had any magnetic fields close to my phone at the time that I did not know of. Here are the concluding questions. What if we did not compensate for magnetic north? How would the results change? I said that the measured x component would be off by the Earth's magnetic north x component. And this would be true for all of our x components. They just become a stronger magnet than if they were separated. So this would make all our calculations larger by a unspecified amount. That is the end. Thank you for watching.